this is a small video as some of you have doubts regarding the theoretical aspect of fractional flow equation. So few of you have asked that what is the exact application and what is the reason, actual reason of using this equation. So as we have discussed earlier about the displacement theory, and it has two components, fractional flow equation and Frontal advance equation. Now we are yet to complete Frontal advance equation. We will cover this particular topic in the next video. So if we talk about fractional flow equation, now fractional flow for any fluid is not exactly the flow rate. This is our block, and let us say this block is partly filled with oil and the majority of box is filled with water, and we know that fractional flow increases with saturation. So we can see that saturation of water is higher in this particular small box. Now water will have some fractional flow and oil will have some fractional flow, and since fractional flow of water will be greater than fractional flow of oil, therefore the movement of water in this particular block will be greater than that of oil. So fractional flow is movement of one particular liquid with respect to movement of another liquid. Now similarly we can define this movement for each and every liquid at each and every point of this reservoir. So this is a reservoir, and reservoir is divided into several blocks, and each block will have some saturation, and depending upon the saturation we can define the movement of oil and water at each and every block. So this is the application of fractional flow equation. Now another thing which we need is the saturation. Till this point we have assumed that we know the saturation at each and every point, but in order to fully understand and accurately estimate the saturation at each and every point with distance from injector well or with respect to time, we use Frontal advance equation. So with the help of Frontal advance equation we will be able to tell saturation at each and every point. Once we are able to tell saturation at each and every point, then we will be able to obtain fractional flow at each and every point, and hence movement or relative movement of oil and water at each and every point. So I hope now you are clear with the fractional flow. Now there are few more things. For example, you have injected some amount of water, and this portion, this is water, and this portion which has not been touched or swept by the water will be filled with oil, obviously. So this portion, this region will be called as swept region. Swept region, and this region will be your unswept region. And this particular portion which divides both of these regions is called as front. So we will do the mathematical analysis of each of these portion once we discuss Frontal advance equation. So the advancing of front is explained by Frontal advance equation. Now let us talk about fractional flow again. Now in order to calculate fractional flow, we do laboratory experiments and we make this plot. So we perform laboratory experiment on core samples and we obtain this fractional flow curve. Therefore, by obtaining this curve, you can know the fractional flow value at each and every saturation. So when you are able to calculate saturation, let's say at this point, with the help of this graph, you will make a plot and determine the corresponding value of fractional flow. You will be able to calculate fractional flow at that particular point. So fractional flow is a function of saturation, and that is not exactly represented in the equation. So yeah, let us talk about the type of questions also which they can ask regarding fractional flow. Now the first type of question which they can ask is the type of curve, whether there is a upward shift, then the process will be less effective, and if there is a downward shift, then the process will be more effective, which we have discussed in the last class. We have taken up each and every variable which can cause upward and downward shift. This is the one type of question. Another type of question can be that they may ask you to form a relation between some of the parameters such as fractional flow and water oil ratio, at reservoir, water oil ratio at surface. So let us take one example. Fractional flow of water can be given by Q and QW divided by QW plus QO. Now if we divide QO, both numerator and denominator, this is what we will obtain, and we can replace this by water oil ratio at reservoir. So similar easy questions can be asked. Similarly, if we are asked to define a relationship, form a formula between water oil ratio at surface with fractional flow, then water oil ratio at surface will be given by this, and which can be written as QW by BW. BW is your formation volume factor, and we can replace Q by FW QT divided by BW, and Q by 1 minus FW QT divided by BO. So this QT will get cancelled out, and FW into BO divided by 1 minus FW into BW. So this equation defines the relationship between them. So easy questions can be asked. First, we have talked about the comparison of graph, upward shift and downward shift. This can be the second type, and lastly, they can ask simple questions, simple formula based questions, because there's nothing much to complicate in that specific equation. Maximum variation they can do is that they will give you the curve of permeability, relative permeability with saturation. So in the question they will mention a saturation, give this plot of relative permeability, and by having the saturation at that particular point, you will calculate relative permeability for oil as well as relative permeability for water. And so once you are able to obtain the relative permeability, you will enter those values in this equation, and finally you will be able to get fractional flow of water. So yes, the fractional flow is this equation does not directly tells the relationship between fractional flow and saturation. It is indirectly defined by these variables, permeability. And at max, to complicate the situation, they can change the units. So if you know how to convert the units in equation, then you can skip the rest of the video. And if you want to practice, then you can follow along. Now in this case, this equation is in Darcy's form. And let's say we have to convert from Darcy's to field units. Now what we can say that this equation, this particular equation is only valid for Darcy's unit. Answers will be wrong if we enter variables value in field units. So we will make changes in this equation according to our need. So fractional flow can be calculated as so if we talk about the permeability, milli-Darcy is the field counterpart and in Darcy's unit we have Darcy. So whenever you are asked to convert, for example you are asked to convert from Darcy's to field unit, you will write the field unit, you will write its counterpart here and divided by the equivalent unit. So basically you have to cancel out this empty part because this particular equation, we are making changes in this equation and this equation is like a machine. Only specific variables can be added into this equation. If you add field variable into this machine, it will reject and it will give you a wrong value. We can only enter Darcy unit into this machine. So therefore we have to cut out the field counterpart. Similarly, area can be feet square. Feet square has to be removed. Therefore, 1 feet has 30.48 centimeter square. Now, I hope you have converted this particular form in drilling engineering. This is in gram per cc and this whole part, this density is in gram per cc and this whole part has to be converted into psi per feet. So while calculating the mud pressure, you might have calculated that 0.433 is the equivalent psi per feet form of gram per cc. So we have calculated permeability, area, and next we have pressure. Pressure can be given by psi in field, and we have ATM. So 1 ATM is equals to 14.7 psi divided by length feet into 30.48 centimeter divided by feet. Okay, so we have missed out viscosity. Now viscosity will be same in both the cases. It will be in centipoise in both Darcy's and field. And next we have flow rate. BBL per day. So let us separate out BBL and day individually. Now every BBL has 5.615 feet cube of one BBL is equals to 5.615 feet cube, and 1 feet cube will be equal to 30.48 cube centimeter cube. And if we talk about the day, one day will have 24 into 60 into 60 seconds. So basically we are converting centimeter per second into BBL per day. So this is the numerator part, and there will be no changes in denominator part because the units will get cancelled out no matter which unit you use. It is the ratio in this case, in both the cases. So once you use your calculator effectively, then you will obtain 1 plus Ka by mu Iw into 0.001126 something. Now let us convert Darcy's to SI unit. Now in GATE, in most of the cases, like they are increasing the number of questions, numerical questions, and they are directly mentioning the SI units. So you need a good practice of unit conversion because you cannot simply keep converting in the exam, as this is a time taking process unless you practice. From Darcy's to SI, now in this case, permeability will get converted to meter square. And this is the Darcy unit. So 1 meter square has roughly 10 to the power 12 Darcy's. If we talk about the area, there will be meter square again. And if we talk about the pressure in SI unit is in Pascal. So one ATM will have nearly 10 to the power 5 pascals. Now there will be a variation of viscosity. In this case, the viscosity will be in Pascal second. Now Pascal second is equal to 1 poise. Pascal second is equal to 10 poise, and it is equal to 1000 centipoise. 1 poise is equal to 100 centipoise. I think they'll take a dedicated lecture on unit conversion maybe in the later phase. So Pascal second here will get converted to centipoise will get converted to Pascal per second. And next we have meter cube per second. So unit of time will remain same, per second in both the cases, and this will be equal to 100 to the power cube. And if we talk about this part, length, then we will have meter here. Alright, so if you do the calculation, now first of all we'll cut 10 to the power 5. This will be your 10 to the power 7. And we'll cut this thing with this. So this will be equal to 10 to the power 3, 10 to the power 2, and you have a 10 to the power 2 again, so 10 to the power 4. So 3 plus 4 is 7. So every constant will get completely cleared out when you convert from Darcy's to SI. So in each and every equation which is mostly related to petroleum engineering, almost all the equations get cut out and the constant will always remain same. Now similarly you can practice this conversion by converting SI into field unit and vice versa.